they don't hear me. Yeah. Okay. So, hello everyone. Today we're having Brandon Hertel's PhD defense. Thank you for coming to his defense. There's a lot of people here. It's very nice. And I see a lot of people on Zoom as well. Welcome. Brandon has been with us since his freshman year, I think. Yeah. And then stayed for master's and then did his PhD. Does his PhD defense. He did a lot of work. Some of the conferences he couldn't attend, although he had a paper because of COVID. But he's going to another conference after this, hopefully. All right. So the structure will be the presentation will go on for 45 minutes to 50 minutes, something like that. And then we will have public questions. Then the public will leave. We have committee questions. And then Brendan will leave. And then we'll have, if he passes, we'll have cake. All right. So I'll pass the sound and everything to Brendan. I think everyone has the shared screen, so everything should be good. Yeah, take it over.
I can view as well. All right. Hello, everybody. Thank you for coming. Thank you for being here if you're here in person. Yeah, it's my PhD defense titled Segmentation, Encoding, Recall, Generalization, and Execution Framework for Learning Robot Tasks from Human Demonstrations. It's kind of a lot, but we'll go through what that means. So I'm gonna start off with the outline. We're gonna go through motivation, thesis statement, the kind of overall framework, and then we'll go into the background of the pieces of that framework, the methodology, how I'm implementing that framework, some experiments, testing the whole framework together, and then finally some concluding statements. So starting with the motivation. So the idea for robot learning is that we want robots to kind of learn like humans learn. We as humans, we do a lot of things without even thinking about it. We can reach towards cups. If somebody tries to knock over the cup while we're reaching towards it, we can pick it up. We can kind of take pieces of things that we've learned and put them together. I learned how to chop onions in one section. I learned how to whisk eggs in another section. I can combine that into making an omelet or something like that without ever having been taught the full making an omelet thing all at once. And we also can synthesize new things. So if I know how to chop an onion, I can probably figure out how to chop like a pear or something. I don't know. But so that's the idea, that we want to have robots have these same capabilities. And we propose this framework for providing these capabilities in robots. So first, we're going to segment big complex demonstrations into simple skills. We as humans, we like to learn everything all at once, but in our head, we're kind of breaking it down into simpler things. We want robots to be able to do the same thing. Encoding, we want to encode similar skills together. So the chopping onions and chopping pears, we get taught those things. We can kind of, classify them as similar and learn from both of them. Recall, we want to reuse encoded skills. So we want to know, oh, I need to chop a pear. Where in my knowledge of skills can I pull from to help me do this? And generalization, we want to be able to generalize to different environments. We're going to use learning from demonstration to do this. And execution, we also want to update. We want to learn from our mistakes, our successes, and all these things. So we're going to use feedback to kind of close the loop of execution. Thesis statement. The purpose of this thesis is to propose a framework for learning robot skills, which can be used by lay users to efficiently teach robots new skills. Additionally, this framework will allow for the reuse of learned skills, synthesis of new skills, and learning from failed demonstrations and executions. All right, I'm going to go through the framework. This is framework, kind of seems like a lot. Just for anybody who saw my proposal, if you see this little robot in the corner, that means that there's new content on the slide. Otherwise, it's the same as the proposal. So we're going to kind of do this in two stages. We have the learning stage and the reproducing stage. Learning stage, we have the segmentation where we're breaking down long, complex tasks into primitives. We're also kind of understanding task structures with this auto HCN stuff. We're going to match the task structures with the primitives, and we're going to encode them into a latent space and store them in this library of motion primitives. When we reproduce, we're going to recall from that library. We transform into the environment. We generalize to that environment and task constraints. And then we execute and we learn from our execution. So we're going to go through each of the background of each of those pieces, and then we'll go through the methodology. So demonstrations, there's a couple different types of demonstrations. There's the simplest one is teleoperation, which is what we're going to focus on here. So that's, for example, controlling a robot with like a joystick, or here I'm kinesthetic teaching this robot. Teleoperation is nice because it's very easy. All you need is a robot and some hands, or robot and a controller, but it does not lead to the best demonstrations. As you hear, the R's I'm drawing are not really great. Sometimes I have to go back because I missed something. We're losing kind of a lot of information from, you have to kind of struggle controlling the robot. It's not like I can just draw the R easily and then the robot sees what I'm doing. That would be shadowing, censored on teacher, or external observation. But those other ones require sensors, some algorithms and things like that. So the operation is kind of the simplest thing, but presents a lot of challenges. But it's the one we're going to be working with here. Additionally, we can have complex demonstrations, which are a sequence of primitives, or just simple skills, which we just call primitives. And we'll be able to handle either of those. Now, complex tasks, they need to be segmented down into simpler tasks because they're difficult to learn all at once. The example I use is if I told a 3-year-old to make coffee, I think they would probably fail at some step. But if I told them, step by step, first we get out the coffee grounds and then we do this. Maybe not like a 3-year-old, but like a 7-year-old. I don't really know children that well. I kind of assume a lot of things, but maybe I was just a really smart 3-year-old. But we kind of break it down step by step, and it's a lot easier to follow, a lot easier to do just one step at a time. Additionally, if we break it down step by step, if we mess up one step, we just have to redo that step. Usually we don't have to redo the whole thing. This is what segmentation allows for. There's some deep learning approaches. There's approaches based on kind of state using hidden semi-Markov models. We also want to understand, ideally, things like semantics, like, the coffee is in the mug versus the coffee is not in the mug. That's, a semantic difference, and you can probably segment based on that. And we also want to ground segments to these semantics. As for a library of motion primitives, this has a long history in the literature of robot learning, going back to like the 90s, where typically it's just thought of as like two systems. There's a perceptual system, what the robot is seeing, what the state of the robot is, like the joint states, and the motor systems, like the actions applied to those joints. It's a kind of very simple understanding this. We're going for a more higher level, kind of think of it as a brain that's storing a bunch of primitives, and that we can access those primitives whenever we need. We also are going to store these hierarchical task networks. This is a way of understanding task structure, breaking it down into a hierarchy. So instead of making coffee being a sequence, just one sequence, there's different hierarchies. So the first one might be preparing the coffee. The second one might be brewing the coffee and then serving coffee. Each of those are broken down further. These have previously been used with predefined tasks. I'm not coming up with these, but we want to be able to use these generally with any task, which we need for the reusability of skilled employments. And then we also want to incorporate when we execute learning from failure. So most LFD methods, that's learning from demonstration. So you gave those demonstrations earlier. We want to learn from those, learn tasks, be able to do tasks using those demonstrations. They only use successful demonstrations. The most common methods, they only use successful demonstrations. They just ignore the failed, or very few can incorporate those failures, but they make a lot of assumptions when they do. So, for example, these DMMs, they assume that it's a close attempt at success. So they are modeling something that's close to failure, but not quite failure. Or these are, TLFSD is optimizing to avoid failure while achieving success. So it's kind of creating a safety bound, basically, on failure. All right, methodology. This is gonna be a lot, so bear with me. This is where we're going to go into each of those pieces of the framework and break it down further into what this defense will be doing. So we're going to go through this piece by piece. We're going to start with this segmentation, which is taking a demonstration. This could be a complex demonstration. We're going to use segmentation to break it down into primitives. And there's two ways that we're going to do this. We can do this without prior knowledge or with prior knowledge. Normally we don't have any prior knowledge. That's where most segmentation is coming from. But because we have this library of motion primitives, we can leverage that prior knowledge to do a little bit better when we do our segmentation. So without prior knowledge, we have this weighted multimodal probabilistic segmentation, which has the very fun acronym of WIMPs. This works best because it's multimodal. So we have a bunch of different data streams from the robot that we're getting together. So this could be where the hand of the robot is, the forces that the robot's feeling. If you have a camera, it could be image flow state, or these kinds of things. The problem is for each of these modes, you have some tuning parameters that you need to define, but it does automatically find those segments once you select these tuning parameters. However, if we have prior knowledge, we can do the same thing. We can do multimodal data as long as the data that we know has the same modes as the data that we're trying to classify. But we don't need any parameters, which is really nice because tuning parameters kind of annoying. And we can do this automatically classification because if we know, hey, we have this prior thing that was chopping, and here's something that is similar to that chopping, this is probably chopping too. And we can also leverage robot-specific similarity metrics to get better results. So starting with the weighted multimodal probabilistic segmentation, it's kind of in the way, but that's fine. So this is an example where we have, should be joints. I don't know where the T went, it's here. But joint data, task-based data, and effector data, gripper data. For example, we have these 4 modes. These are pretty common that you would get these in any robot, at least if it has an end effector force sensor. We run change point detection on each of the modes. We get the change points for each of those modes. We probabilistically model those change points, and then we do this weighted combination. We sample from this kind of overall, we get a probabilistic probability density function, and we get these final key points. So what that looks in practice is something like this, where we have this task where we're taking the robot, picking up a plate. We have to kind of press the plate against the side of the wall to be able to pick it up, and then bringing the robot back. So we have these 3 examples. This is just using a single mode. This is using only position data. This is using all of our modes, but we are weighting them uniformly. So we're not leveraging the weighting of this task, which force data is going to be pretty important in this task because we're pushing that plate against the wall. And here is where we're weighting force higher than the others. So you can see this results in the kind of nicest, most intuitive segmentation. On the other ones, you get some these weird segments that don't really mean anything. And we do this across a whole data set of tasks like this. We do this across 60 tasks. And these are the specific weights of those modes. With the custom weights, we get the nicest. We're looking for 3 to 4 segments here. So you can see 1, 2, 3, 4. Sometimes these first 2 get combined into 1. So 3 to 4 segments. Anything more than 4 segments, you're over segmenting this task. So you see the position only and the uniform weights, they over segment this task, whereas the custom weights are within that nice range. They also provide a more consistent segmentation across the data set. And then if we have prior knowledge, we can use this parameter-free correlation segmentation. So we are given some long horizon demonstration. This could be, making coffee, right? And we know parts of it. We know how to pour coffee, and we know how to press the button on the coffee machine to brew the coffee, for example. If we know those things, then we can look for them in this long task and say, okay, these are where the segments should be, and also this is the class for these pieces of the long task. So what this actually looks like in the algorithm side of things is that we have different similarity metrics, and we're just testing. Is it hard to see?
Just for me.
Okay. We're testing the similarity metrics for our known tasks compared to the new task. And we're finding the similarity. We test 3 similarity metrics. This is it's based on something called cross correlation. So this is the typical cross correlation similarity. This is something that's used in like radar and stuff. So maybe not the best for robot tasks. We test the negative sum of squared errors. It's just sum of squared errors, but negative because we need a higher is better metric. And then the cosine similarity. So this is measuring the similarity in shape. These are the tangent vectors of these. Let's come up with it. But And then we're testing all three of these, we're finding the similarity, and then we just segment based on the maximum of this value. So what we do is we have these known classes for this setting the table task. So we pick up the plate, place the plate, pick the napkin, put the napkin down, pick up a cup, put it down, pick up a fork and spoon, and so on. It's setting the table. So we take one demonstration of just each of these primitives. We have this kind of known set of known tasks, and then we segment. So we also test with and without smoothing. This is just a little bit of pre-processing, pretty standard. Does require some parameters, but this is something that is done in most with most robots, so it's not necessarily a bad thing. And we find that with the smoothing and the cosine similarity, you get over 90% accuracy with our segmentation. There is some pieces where it maybe cuts off our this plate task a little bit early, but that can happen because of varying lengths of demonstrations. So over 90% actually pretty happy with that. Next, we're going to go into this auto HCM piece. So we want to be given a high level description of the task, like something like one sentence, making coffee, something like that. We're going to break it down and automatically discover the task structure of this task. So first we have to kind of understand the structure that we want. So we're going to use this recursive definition task. So we want to know if I'm a task, if I am brewing coffee, what are the subtasks, what is in the hierarchy level below me, what are the preconditions, what should be done before I do this task, or the post conditions, what should be true after I complete this task, whether this task is optional. For example, making coffee, sometimes we will automatically get the task of like adding creamer to the coffee. That's optional, not everybody wants cream in their coffee. And also the parent task, what's in the hierarchy level above me. I mean, I want to be able to plan and execute these tasks. And so we're going to store them in this kind of recursive tree structure. So how do we automatically learn these? So again, these are previously used for predefined tasks. We're going to automatically build them using a LLM prompt. So the user basically says something, I'm going to show you how to set the table. We take that setting the table, we send it off to an LLM using a prompt. We say, hey, how do you do this task? Give me, this format basically. And then we want to be able to use that, get back the task structure. We also need these subtasks to be not unique. So for example, pouring into a mug, that could be in making coffee and making tea. We want to be able to access both of those. We want to be able to evolve these HCMs over time. So if we are shown making coffee, and then we are shown it again later, but there's maybe an order that's slightly different, we want to be able to kind of merge both of those together. This is kind of essential for that reusability. So this is kind of this process is a piece of the framework that is just focused on this auto HCM part. So we are given our demonstration, we do the segmentation that we already talked about. We put the segments and primitives into the library. We take this task description, make this auto HCM. We encode or embed that description with those primitives, and then later we can recall, plan our task. All right, so we'll go into that kind of encoding piece because that's where the motions and the descriptions are matched together. So we want to encode like skills. For example, here we want to perform a reaching primitive. What demonstrations that I know, what should be used? What if I don't know any reaching demonstrations? So the idea here is that we embed these skills. We embed skill descriptions, which we got from that HTN, into a latent space. We use a sentence transform from this. These are pretty common models. I don't know if people have heard of BERT. It's an example of this, of a sentence transformer. And then when we need skills, we can use the same idea to find similar skills. So what this does is it will take this context, encode it. It will code into like 700-ish just numbers from like 0 to 1. And that becomes our latent space representation. And then same thing later. We take something, encode it, get 700-ish numbers, find the most similar skills that we know, and that will give us our most similar motion. That might seem a little weird, but here's kind of what that will look like in practice. First, we want to make sure that this works. So we take a couple different sentences. These are the things that will get embedded. So we have a high-level description of the task and a low-level description of this specific action. So we can just say high-level, low-level. There's some others with a little bit of fluff here. There's sometimes where we're including whether it was successful or not. And then we have these different sentence transformer models. These will, again, just give us different sizes of embeddings, different sizes of models, different training data, different architectures. And we want to see which of these combinations works best. And what we find is this model 1 and sentence 3. So this is the MPNet here, and sentence 3 is a high-level skill, and then that tells the high-level skill, and then the subtask. So it's the subtask. We find that this has the highest correlation. This is, we're measuring embedding similarity to a sentence similarity, or sorry, not to motion dissimilarity, which is why we want a higher negative correlation. We can make this positive if we were just doing similarity, but we also use this reassemble data set, which will come back in like 2 slides. So here, now we want to recall those same skills, which again, we can use the same process of that sentence embedding. So again, we're getting this auto HTM when we need to reproduce, and this provides those sentence description or that task description, which we then embed, get similarity. So this is an example on this reassemble data set. This is an assembly data set. I think they're assembling IKEA furniture. So what we do is we withhold this one skill that's in the data set. This is the only example of the skill in the data set, and we kind of hold it out. It's this pick small gear lift skill. And we say, and we embed the rest of the data set using that same process. So we have this library that has all of this data set, the motions, the embeddings. Now we embed this pick small gear lift. We just get the encoding for that. We get that 700 numbers or whatever. And we say, which are the most K similar other 700 numbers that are in the data set. So we do K1, 2, 4, 6, 8, and 10. And what we find is that 1 and 6 get pretty good results. So here, this green is the thing that we withhold, the thing that we don't know. The gray here, that's what we are given when we use this process. So you can see here we're given 2 different ones, 3 or 4. Okay. So the red is then what we are able to reproduce from the gray that we're given. So you can see we get pretty close to the green. Again, we've never been shown what the green is. We're able to synthesize that skill from other skills. Does that make sense? Okay, so this is kind of pretty a central piece of it. So yeah, with this, we can, without ever having been shown something, just being shown something that's similar, we can be able to do this unseen new skill. All right, and then once we get those demonstrations, those new demonstrations that we want to reproduce, we need to generalize them to different environments, right? So we have proposed this method for learning from demonstration called elastic maps. It has a lot of extensions that we will go through all of them, but we're going to start with the kind of baseline version of it. Essentially, we have the data, the demonstrations, these little orange dots, and we want to model those data using a series of nodes, which are these blue dots. We're going to connect data to nodes with springs, and we're going to connect nodes to each other also with springs. 2 adjacent nodes is an edge, and 2 sets of adjacent nodes, so 3 nodes together, is a rib. So we have 3 energies. This is the approximation energy. It's measuring the energy in these springs of these orange ones, connecting them to the nodes. The stretching energy is measuring the nodes together, and the bending energy is the ribs. So, if I stretch the spring, it will spring back. If I bend a spring, it will also bring back. So these ones are the stretching, and these 2 are bending, but they're stretching different things. We minimize all these energies together, and we get what's called an elastic map, which happens to have some really nice features for robot motion. It's nice and smooth. It promotes evenly spaced nodes. So that's a very easy velocity or constant velocity for the robot to follow. Yeah, we can also easily add in constraints. We can handle any number of demonstrations. We can do other things that we'll get through. That's why there's all these extensions, because it's very, very nice and flexible. So here it is. This is the Lhasa data set, the handwriting data set. The gray is the demonstrations, and the red is the elastic map reproduction. So you can see here, just one demonstration models it very nicely. Multiple demonstrations with constraints as well. There's sometimes where it gets these kind of cusps when you are meeting a constraint that's kind of far outside of the demonstrations. There's an extension that we'll go through that will kind of fix that. So the first extension is pretty simple. We're going to modify the optimization to work online. So here we're just optimizing over the whole map. That's this Y. But here we're optimizing only over the portion of the map that we have left to execute. So what we can do is, if I'm reaching towards a cup and somebody moves the cup, I can update my execution to follow that move. We also show that there's two ways to do this optimization. Can either do EM, which is expectation maximization, or this convex optimization. The convex optimization has a more linear growth rate in time. I mean, this is like, tenths of a second, so it's not a huge difference, but the convex optimization, the more consistent for this purpose. We also look at so I can like move it over here. Okay. Yeah. This elastic Laplacian trajectory editing. So what we're trying to do here is maintain the shape of demonstrations. If you look here, it's really caring more about the actual position of things rather than the shape. You see, if it maintained the shape, we wouldn't have this kind of very I think this is like the snake shape. This is very unsnake-like corner here. So we want to maintain the shape. This is also really good if we're adapting online. We want to be maintaining the shape as well. So what we do is we transform what we're trying to model into Laplacian space, and then we use that for our approximation energy. So Laplacian space is this, essentially what it does is it's a way of representing the shape of a curve. We also do this clustering in matrix form. So what this looks like is, if we are given this black trajectory, we start here, we're following the black, and then at this point, at the star, we change it to one of these 4 new points. We adapt really nicely, again, maintaining the shape. We don't end up caring about the actual position at all. Same thing, we compare against dynamic movement primitives, which are very common. Learning from demonstration method. I can work with only single demonstration as well. If this were something like somebody was moving a button or something, and you had to press a button here and press a button here, we keep this nice corner, or maybe you're welding or something like that, and somebody moves the piece. Whereas DMP, they don't really keep that same shape. They also have this overshoot here, going through weld sharp corners. So yeah, we're able to adapt really well to the new shapes. Have another extension of this is that we can include these other coordinate spaces. So we included the Laplacian space. Here we're including the tangent space, and then also the Cartesian space. So we're optimizing over the Cartesian approximation energy, tangent approximation energy, Laplacian approximation energy, and then also the stretching and bending. And kind of this is maybe a more complex version of it, but if we set some of the weights for these to 0, or just some of the values for these to 0, we get the baseline or ELT respectively. And what this also adds some more weighting parameters, because we have to weight all these together. So what we can do is we can estimate these weighting parameters. We estimate based on the importance, which is this alpha, and a scaling factor beta. As you go into these different coordinate spaces, they'll have different scaling, so you want to rescale them accordingly. That's how you get these scaling factors. We're just taking it's just a normalization basically. And the importance is from this minimization over our cost function here, which is just the unweighted approximation of the Cartesian space. And what this results in when you do this importance weighting. So again, this is lost data set. We have this N shape here, a couple different demonstrations. If we just have this uniform weighting, we don't do the importance weighting of the different coordinate spaces. It does this kind of jaggedy motion where it's trying to match the Cartesian things because there's a lot of variance here. So it's trying to model all of it. Whereas when we do this importance weighting, we see that the shape is actually the important thing for this, for these demonstrations, and we maintain this shape nice and smooth. We don't care about, exactly matching this point out here or something like that. We can match the shape of it because that's what's important. And this is an example with a real robot. Again, this is if you remember, I was drawing those R's earlier. It gets this really nice, smooth reproduction, even though my demonstrations were not so good. We're very jaggedy, but overall, with just 4 demonstrations, it sees that kind of the common theme among those is the shape, and we can reproduce that. Next, we include forces into the elastic maps. So this is a very kind of simple inclusion or very natural inclusion. Obviously, the springs are based on forces and energies. So we just can model the forces that the robot feels as springs using Hooke's law. We essentially are just defining this W, the spring constant of whichever point we're modeling according to this approximation. But we need to make things directional now. Oh no, it's kind of back here. Everything is just these points are directional, but the weights and things like that are scalar values. But forces are not always scalars. They should be directional, and so we need to make the forces directional as well. So we, for example, X, Y, Z, if you're keeping everything uniform, it would be 1, 1, 1. But for forces, we need to use this Hooke's law, model of forces. And then we also include this Hadamard product, essentially a way of keeping each dimension in its own dimension. We're not mixing X forces with Y forces or Y position or anything like that. We also need this now L2 norm on the weights because they are vectors. So what this looks like in practice is we have this setup where this user is using a VR controller to control the robot. We did this because you don't get any haptic feedback with this controller. So with, if I'm using my hands to push a button, we have this button here that the user is attempting to push with the robot. If I'm using my hands to do that, I can feel when I'm applying too much force. With this remote controller, they don't get any of that feedback. So it's very easy to apply way too much force. I actually hit the E-stop a couple times while trying to get this demonstration. So you can see here, we get this huge force spike in the demonstration when the user is pushing the button. The spike is around 85 newtons. You do not need 85 newtons to push a button. If you do, you probably don't need to push the button. So you see here, we model these forces, these little green arrows, and adapt the trajectory preemptively before execution to avoid these unnecessary forces. In execution, it pushes the button. We see I think it's less than 20 newtons of force. So much more reasonable and less likely for the robot to break with a much smaller amount of force. Same thing, we have this erasing task. So erasing is interesting because you need to apply some force to actually erase whatever you're trying to do, but you don't want to be applying too much. We also here are using that segmentation that we're talking about, the weighted multimodal probabilistic segmentation. So we're breaking this down into 3 segments: the approach, the erase, and the retreat. And then we still are able to erase, and we have a much smaller force profile. The peak forces here are about the same, but overall we're feeling much less force on the robot and only applying kind of what we need to. All right, and then we also have one last piece of it where we haven't included the learning from failure yet. So previously we assumed that all the weights are positive. Basically, we want to model all the data that we're given. We also are assuming that these stretching and bending parameters are all the same. just makes the math a little bit easier. But that's not necessarily an assumption that you want to keep. So what we do is we include the ability to learn from failure and the automatic adjustable stretching and bending parameters. For this, it's actually a very simple update. All we have to do is put an absolute value on the normalization factor. Otherwise, updating the approximation energy works with negative weights. As for the stretching and bending parameters, what we want to do is when we're in a region that has a lot of failure or that doesn't have a high amount of weights, basically, want to loosen or we want to tighten our parameters rather. That means that we want to be very stiff in unknown regions. And in regions that we know a lot of information where we're modeling good data, we can be a lot looser to more freely model that data. That's essentially what these update rules are doing. So what that looks like, these are some examples of different cases for learning from failure. So this is the trivial case where there's only successful data given. This is kind of the case that we've been looking at so far. This is a case where we're only given bad data is actually very hard because you don't have any good examples. You don't know what you're supposed to be doing. And all of these, the obstacle is not known to the algorithm. You can have mixed, you can have different modalities. So multimodal success, multimodal failure, they can be both multimodal. You also have continuous labels for demonstrations. So some demonstrations could be better than others. For example, this one is pretty far away from any obstacles, whereas this one is pretty close. So this one that's farther away would be better than this one. We can have pieces of demonstrations which are bad. So here only the pieces which are interacting with the obstacle are bad, and then we can combine these two to have this. It becomes almost like a field of positive and negative weights that we can model. We won't be able to handle all of these cases, basically. Some of these cases, these are requiring more effort from the user, or maybe you have like a task definition that can automatically find these, whereas these kind of simpler labels are much easier for a user to provide. So what we get here is in the orange. So you see for this first case, pretty simple. We just follow the green line. Here we don't know what to do, so we just go straight to the end, which we go through the obstacle. It's bad. You don't want to be doing that. We will discuss this more on the next slide and how to avoid doing something like this. We see for all these other cases, we provide pretty good reproductions, especially like these last two where, we're just going right around the obstacles and really modeling success very nicely. So when you are presented with only failure, what we want to do two things. One, we're going to do an exploration phase. Basically, what we want to say is we're going back to that assumption that failure is a close attempt at success. So what we do is we pretend that there's a noisy good demonstration for each of these bad demonstrations. And then we run our algorithm based on this. So you see, it doesn't always provide a good result in the first time. We start hitting this corner here, but then we can update. We say, okay, well, that one wasn't good. We'll try again. And now we have 3 bad demonstrations. We again we look at noisy good demonstrations, and we find this really nice reproduction that avoids the obstacle. There is, maybe you don't want this. You could add further iterations to eventually get a result that does not have this sharp corner in it. And we do this with different numbers of obstacles. It will take more time the more obstacles there are, just because it's harder to find a successful reproduction. But theoretically, given infinite tries, it will always be able to find a solution if one exists using this method. So that's failure. That's kind of all the pieces. So we're going to put it all together. We're going to have these 3 approximation energies that we talked about. Just the Cartesian approximation energy. We have vectorized weights. We can include failure, include forces, all these things. The tangent approximation energy, Laplacian approximation energy, same thing. Here we just are converting the demonstrations into the tangent and Laplacian space first. And then also the stretching bending energies. These are vectorized, and you can automatically update them using the update rules that we talked about earlier. we bring it all together in this minimization, and you get a really nice elastic map production. Yeah. We are automatically kind of learning all the weights here, which can be good, takes burden off of users, right? But that might not always lead to kind of a reproduction that the users want. Oh, yeah, sorry, this is still on the last slide. We can automatically update beats, like I said. So what we want to do is be able to tailor reproductions to user preferences as well. So we performed a user study where they could select the weights of, this is using the MCL map, just to simplify things a little bit. So they can select the weights of MCL map according to their preference. We perform a meta optimization based on these three objectives. This is a spatial similarity, the shape similarity, and then smoothness. So users are balancing these three. This is the meta optimization where these are the weights. These are just the MCL map weights that we saw earlier. And what we found, or we designed this UI, it's maybe a little bit hard to see. There's a lot going on, but essentially they're given, here's these three options. This is what it looks like in a 3D plot. They could preview what it would look like on the robot. So they would be presented three options. We gave them three different options. They could select one of them, and they would be presented with three similar options. So there's kind of this wide spread into a smaller fine-tuned spread. And then if they selected an option on the second screen, got ran on the actual robot, we did a set of three different tasks. So there was a pick and place task where there was a cup in this dishwasher, generously lended to us by the ARA lab. They would pick the cup out of the dishwasher, put it on the table. There's this pushing where they would push the dishwasher drawer closed, and then erasing, we drew a shape on a whiteboard right next to the robot, and they would erase that shape. So we want to examine preferences across users and across tasks. So first, across tasks, we're hoping for kind of a consistent preference. They'd be like, all tasks users want to see the robot do or perform in this way, and then create like a metric and a measure based on that metric. We didn't find that. Instead, we found varying results. For example, so for here, this is the spatial, or this is the shape, and this is the smoothness for all the tasks and overall. Lower numbers here, the first number here, a lower number indicates a higher preference. For the second number here, this is the standard deviation. A lower number indicates a more consistent preference. So what we see is across all the tests, smoothness is consistently the most preferred. And then with the spatial similarity and then the shape similarity. But for each task, it kind of depends upon how much. For example, in the pick place, smoothness was by far the most preferred and the most consistently preferred, right? So in the pick and place, the actual shape doesn't matter too much as long as it actually picks up the object and places it. So, you might as well just make that motion as smooth as possible, basically. For erasing, here we see a pretty big jump in the shape similarity. This is because we drew an S shape, and everybody wanted to erase the S shape in the shape of the S instead of just like racing it up and down. So there was a higher preference for shape similarity with this task. So this kind of means that we can't really create this overall preference across all tasks. We kind of have to tailor preferences on a per task basis. Then for users, so we have a 3D preference space, which you can kind of see in the corner here. This is 4 different users. We did a study of 20 users, so we selected 4 of them here. You're seeing this 2D representation of this 3D space. This is generated using PCA, or principal component analysis. And then we're showing they had 5 preference selections. You're seeing these 5 preference selections as these dots here. And then we use a support vector classifier to kind of create the colors to show kind of where a preference space is. So essentially, some of these users had an overlap, basically, where their preference spaces were essentially the same for tasks. This user, there's not really an overlap, but the preference was pretty much the same throughout the entire experiment. Whereas some users, they have like these pretty clearly defined regions. Like here, this is the purple region, green region, purple region, green region. There's not a ton of overlap between them. So what we did is we ran an analysis based on kind of where these dots land in this preference space. The minimum of the green dot to the purple dot, maximum green dot to the purple dot, and then the mean, the average over all of them. If there was a trend, you would see not such big spreads as we see here, basically. This shows that different users kind of, they have very unique preferences, and we need to tailor reproductions to each user's individual preference. So that means, one, like exploring that in the user. This was a human in the loop experiment, so forming that kind of same human in the loop preference finding. And we also need a very flexible learning from demonstration representation, which Elastic Maps can do. We had a question in this experiment saying, do you feel like your preference was represented accurately? And we overwhelmingly got positive response to that. So we can kind of understand that Elastic Maps can perform this, can be tailored to user preferences. Okay. Onto experiments. This is going to bring it all together. I know it's been a lot of content, but hopefully these will make sense. So we're going to start. Very simple task. Writing hello. This is on a 2D keyboard and mouse interface, not using actual robot yet. So hello, just drew it with a mouse. This is we don't have any prior knowledge. We use the weighted multimodal probabilistic segmentation. You see it's not perfect. Some of the H kind of, the E starts a little late and the H is a little bit extended, but that's okay. It will still probably work for our means. So what we can do is kind of internally, everything gets normalized. So if we just reproduce things according to the internals, it's a really big E because it's a really small shape. We also have this like slanted writing here, but we can apply constraints to, we can apply constraints to fix that. The E still looks a little bit wonky. I could probably spend some more time figuring out constraints, but you know, this is just showing that, you know, we can have this complex task, break it down, store it in the library, and then reproduce it later. What we can also do is reproduce things that we've never seen before, but have the building blocks of that complex task. So we can also write different words using those same letters. E actually looks a lot better in this one, I think. But we can kind of understand things, right? We're understanding task structures, we're understanding components. We're not just kind of blindly reproducing what was shown to us. Now to put that into 3D, so we did a cup stacking test of these set of 5 cups. We had a user pick up one cup, store into the next. So what the demonstration looks like, it's just a series of 4 pick in places. I think there's 1, 2, 3, 4 pick in places. We segment it into those 4 pick in places, and then we reproduce it again. So now we're using auto HTN. This is what the HTN gives us. It gives us also these 2 first ones, pick up base cup and place base cup on surface, which we don't actually need because those are already done in the environment. So we can kind of ignore those. We mark them as optional, and we use the other 4 here. So we have the user demonstrate the 4 picking places. You see there's a lot of like jiggling to try and like line up the cups with each other. Also here, the user does a different grasp for this set of cups. Technically, HDN does not perfectly model this task. It has it backwards because we're putting nested cups into a cup where it says put a cup into the nested cups. It doesn't actually matter. We're able to understand it. Just you can see this is the reproduction. Nicely picks up all the cups, stacks them, and this is like a pretty simple task. I'm hoping 3 to 7-year-olds should be able to do this also. We I think it's hard to see in the demonstration, but the user kind of struggled with this last place, but this one does it nicely. Yeah. So we're gonna try, I guess, with more complicated tasks. Okay. This is making coffee. This is a lot more complicated. This coffee machine has like precise pieces of it. It's like this. Hole for the K-cup is kind of tight. I have to position it really nicely to put it in. The button here also is very small. I have to wait to press it. We're dealing with liquids. We don't want to spill any liquids with the robot. Has to wait to brew the coffee a little bit. So this is a demonstration. I'm kind of in the way sometimes, but you can see hopefully that there's coffee at the end of here in the mug and sheet. So now we break that. We use the auto HDN to create this hierarchical task network. And we get these. We have to be a little bit specific. We say making coffee with a K-cup. If you just say making coffee, it gives you different instructions. But we get those nice task definitions, break it down, and we do this reproduction from this HDN. And the robot is able to reproduce this task. Again, this is with all these kind of precise motions. Does crunch the K-cup a little bit, but not so much that it stops working. Yeah. I don't know what that was. I know it's not while editing. Yeah, that's the wait brewing coffee. There's one thing to note is that we so it's waiting until preconditions, postconditions are satisfied to kind of move on to the next thing. Right now, because I'll talk about this later, not using a visual module. So I'm the one there saying, yes, this precondition or this postcondition is satisfied, but ideally you'll be able to automatically do that. So again, here, there's some coffee in there, which I did not drink because I don't drink coffee, but I'm sure it tasted fine. So that was, a little bit more complicated task than the cup stacking. It's able to do it well. And here we're gonna go back to a simpler task, but we're gonna try and show something a little bit different. So this is decluttering. So there's this mug on the table, and we're putting it in the drawer, and then we're gonna close the drawer. So we're gonna give two demonstrations. The first, I'm gonna push the drawer kind of slowly, and with a pretty constant wrist angle. And the second one, I'm doing like a flick. I accidentally move the drawer into place. So I'm going to flick the drawer closed. And then we're going to learn from both of these. And the first time it learns from both of these, it does some weird combination of the two where it slowly flicks, which does not work, right? So we're going to look at learning from updates. Also, this kind of weird back and forth that it does, that's a bug. I fixed that. It's all good. But it didn't affect the actual results. Yeah, it does it here too. Yeah. And then we also, I don't know if maybe you noticed, but we also changed the starting position of the month. Yeah, you see here, it kind of just does this thing in space where it doesn't even touch the drawer. And so we incorporate that into the model. We say, okay, those first two things you did, those were good, but this last thing was bad. And then update based on that. So here we're learning from 3 tasks instead of the 2 before. Same thing, it can pick and place the mug just fine. It got reinforced successfully with that. It has to do, this bug has to do with the timing of constraints. Yeah, fixed it, I realized. And so here it closes. It says, okay, I tried to do this flick thing, this weird flick thing last time that was above here. So that was bad. I'm just going to stay down here, and it ends up following the first demonstration pretty closely and ultimately successfully. In conclusion, we have proposed the SERGE framework. We have introduced several novel components. So the segmentation, 2 segmentation methods, the encoding and recalling skills, the learning from demonstration, and then the synthesizing new skills as well. And then we've also have an implementation and validation of this framework. yeah, the code will be available at some point when the thesis gets okayed. There's a couple avenues for future work here. First is detection identification. So we're just learning from failures here. We're not identifying them. We're not saying why this failed. We're not also online saying, oh, this is bad, stop, and then relearn. We don't handle failures kind of online. So these are kind of important things that if you were to deploy this in the real world would probably be needed. A vision module, like I said, not using vision here. We kind of simplify this. I say we use AR tags to say this is the position of this thing, or I just tell the robot here's the position of this thing. But online full vision module would be necessary for real world stuff. Grasping module as well. So right now it's just doing the graphs that I showed it, which for example, I'm using a mug. If I were to change the type of mug or the bottle or something like that, you would want a grasping module to be able to adapt to that. It would be able to generalize a lot better than the LFD would be able to be. And also finding an alternative to auto HDM, it works, but as you can see, it sometimes gives us unnecessary pieces. Also, it will give you can give it the same prompt twice and it will give you two different responses because it's an LLM. So just something that's a bit more consistent, ideally, for the real world implementation. Yeah, there's a list of publications from this while I was doing this PhD. Most recently, this IROS paper that will be in October in Pittsburgh. Oh. Yeah, thank you. That's it. Yes. Yeah.
All right, great presentation. So now time for public questions.
Yes.
Was very so you actually mentioned that in the conclusion, I was waiting for it, and you actually mentioned that about LLM giving different responses. But I have a question. Do you think the subtasks for a human, like imagine a human is doing a task and a robot is supposed to do the same task. Do you think the subtasks would be like identical?
So no, not necessarily, right? The kind of key idea here, I can maybe show you as well. I don't think I include here. Great. No, I did not. But there are things that, like I said, it gives us back these kind of things that we don't actually have to do. So here, there's some optional tasks that like is like gather ingredients and like turn on the coffee machine, stuff like that. Things that the robot doesn't have to do. So yes, right now I go in and I mark those as, you know, I say they're optional, but they're probably not something the robot will ever have to do. So yes, there's I do a little bit of cleaning up, but for the most part, it's automatically discovered. Another thing is if we are since we can do this matching, if we have a known task that is like open something, we can just say, oh, well, I see this part that's open, and in the HDM, there's these other tasks first, but here the actual demonstration given starts open, so we know just to start from there. So we can do this automatically if we have more information.
Yeah, so I think you said, oh, we send the query to the LLM and we get the subtasks.
Yeah.
That's where like the entire thing can fail. Because,
So
because there are no LLMs that are trained on a giving an answer for a robot.
Yes, that is true. Actually, I think I have some here. So this is just making coffee. So yeah, like one, it gives different responses. For example, these two, it ends up giving these two HTMs basically. I showed them in a more compact fashion here. Kind of the major pieces are like the same, but like there's some minor stuff that is different. So yeah, like I said, it's unreliable. It gives you things that humans are meant for. Like I think actually in this version, it gave me one that was like after serve coffee, room cup. I think it says enjoy coffee, which robot's not allowed to enjoy coffee, unfortunately. But yes, this is definitely the piece where it's not quite perfect. Yeah.
Thank you, Brandon, for the good presentation, the great talk. When you were talking about the cup stacking and the coffee making example,
Yeah.
at least Sam and I, when you put the first cup in the second cup, it got very close to not getting into the cup.
Yes.
What is your experience with regards to something that is like very close to something that can fail compared to like the movement in space to move between cups? Because if you move higher or lower in space, it doesn't matter that much.
Mhm.
But if it's like the cup really has to fit perfectly in the cup, it's a very more subtle thing. How was your experience with that closeness?
Yeah, so actually, with the cup stacking, it didn't have any issues. I know it looks close, but like that was my first time running that actually. And it just did it perfectly first try. And it like struggled less. This is just some they use doing it. Like she struggled a bit. She took like 5 demonstrations before she was happy with the one that we went with. But like the first pre-production, it did it just fine. I know that it was like a little close, but it ended up being successful, so I kind of went with it. But you can then, if you're not happy with it, you can add it back into the library and do that update thing. So, but you also don't have to add it in as fully successful. You could add it in as, you know, slightly failed or something like that. Here in my examples, I just did fully success or fully failed because it's easier for people to give those labels. But theoretically, it could handle those more fine-tuned labels. So that would be how you would handle it.
Okay. Cool. Thanks.
Thanks for the presentation. Just a quick question on the HDL.
Yeah.
So how would you map the subtasks to the skill, and sub question is, do you have like, does the HDL give you pre and post condition when the
Yeah.
skill is satisfied or not?
Yeah. So here I can actually so this is the actual prompt that I use. So I tell it, here, give me the preconditions and post conditions and mark them with asterisks and carets, basically. And it does do that. It does give me those pre and post conditions. I just don't show them here because otherwise this would be like huge. There's a ton of information. But like some of these are like, water is in the cup, coffee's in the cup, you know, cup is empty or cup is in the filter or something like that. So it does give me those, right? As for the matching is actually a problem that's kind of hard. If we don't have, so this goes back to the segmentation, because you segment, I have it up. Because you have the segmentation, so you have these primitives, and you do the automation, so you have this hierarchy. You have primitives, you have the HCM, and you're trying to figure out how to overlap them. If we don't have the prior knowledge, you can't really do much. You just have to kind of go in blind, right? You don't know this is what a picking place looks like. This is what a button pressing looks like. You just kind of have to blindly match it up. If you have that prior knowledge, what you can do is it's a dynamic programming problem, I guess. It's like a it kind of, if you know how dynamic time warping works, it's basically like where you say, I have this list of actions for what the HTM says, and this list of actions for what my primitives say, which I get from the parameter feed relation segmentation. You do them, and they might not exactly be the same. One might be pick cup, and one might be grass cup or something. But what we do is we actually use the same sentence embedding model to match the embeddings, and basically you want to optimize that matching. I did not go through that, but it's something that I thought was going to be easy. It turned out to be harder. So yeah.
So I'm a bit curious on, this is mostly for what humans can do, correct?
Yeah.
So how would you go about teaching a robot to do something that either humans can't perceive or too fast to do, or let's say like something is really heavy, like let's say you want to move a car from one place to the next via lifting and not actually operating a car. How would you go about teaching a robot to do something like that? How can it be adapted for such a thing?
I think Probably not well. I think it's the answer. This is more intended for like household things, repetitive tasks, these kind of things. If you wanted to do something that is kind of a more specialized thing, you're probably better off using other methods for that, I would say. This is trying to be general. Perhaps it could be adapted, you know, the same ideas of breaking down complex tasks and, you know, adapting them to your environment. I think they can be pretty generally applied. But for something that would be like very specific, for example, yeah, you need a robot to like operate some like complex piece of machinery. You know, it would be probably, this is not the greatest framework for that, I would say. This is trying to be more general and lightweight.
Other questions? All right.
Thank you.
All right, now we ask the public to leave and stay around if you're on campus for later. For people on Zoom, thank you for joining. Yes.
Yeah.
I will